Today we're going to look at artificial intelligence, reinforcement learning, and sequential decision problem. These two things are intrinsically related. We're going to untangle this. Okay, the references for today's class are first, again, the book for the class, Probabilistic Machine Learning for a Civil Engineer, chapter 14. Then Russell and Norvig, chapter 17, and the complete book from Sutton and Barta, which is an excellent reference as well. So first, artificial intelligence. We hear often about it. What is it really? Okay? In a generic, simple way, it's the reproduction of an intelligent behavior by a machine. And here, a machine is not necessarily a physical machine. It can be simply a computer. Okay? So here, the goal of this AI is to perceive the environment, interact with it in order to make a sequence of rational decisions. Okay, the same rational decision we saw in the previous module when we were talking about utility theory. Okay, when I'm talking about artificial intelligence, of course, this is not what I'm referring to. Okay, I'm more referring to examples such as IBM Watson can play Jeopardy. We can have computers that's going to play games either from Atari or Super Mario, or more complex examples such as AlphaGo, which can play the game Go better than any human on Earth. So in that case, all these examples refer to what we call level 1 limited artificial intelligence. It means that we go beyond human capacity, but in a single specific task. Here it's playing either of those games. So here behind that limited AI is machine learning. This is what's powering that artificial intelligence. So we can really see machine learning as being part of the field of AI. And as we've seen throughout this class, what is behind machine learning is going to be probability theory, decision theory, linear algebra, optimization, etc. Everything we've covered together. Okay, so now we're going to look at the relationship between artificial intelligence, sequential decision, and how the missing link in between is going to be reinforcement learning. So reinforcement learning is one of the subfields of machine learning where we want to learn without being supervised. Okay, it means we want what we're going to call an agent, so a computer, to learn how to act in an environment. And an environment could be, like in this example, a game, Super Mario. So how does the computer can learn to play Super Mario without being explicitly told how to play? What does it mean? It means that the person who's going to program that reinforcement learning is not going to explicitly say, if you see that obstacle or that enemy, do this action. Okay? We want to have a computer program or an algorithm that will figure out on its own what are the actions to take given the state of the play by playing repetitively and by doing trials and error to see what are the optimal action to take in order not to maximize the current benefit, so the current reward at time t, but the long-term horizon of either finishing the game or maybe maximizing my score through that game. Okay, so we want to develop the mathematical framework that will allow us to do these kinds of tasks, making a plan for action that is going to maximize the long-term game of play. Okay, so to put more framework on this, in this case, we're going to denote by this calligraphic letter our set of action S, or set of states, okay? So in this case, it's going to be our environment. So in this case, our environment is going to be, in this example, the Super Mario game, okay? So this is what we're considering here in this case. Then we have a set of actions. Okay, what are the actions Super Mario can take? So the computer will have to choose from all the possible arrows and the A and B button. Okay, these are the possible actions the agent can take. Then S of t is the state of the play at time t. Okay, it's the relative position of Super Mario in the game with respect to the thing it can collect, the obstacle, or everything there is around, okay? And here, the state of the system is actually, again, what is the relative position of Mario with respect to everything there is in the game. And the reward is function of that state. So how good is it for Super Mario to be in a current position? Okay, with respect to everything, with respect to what has been collected. Okay, this is function of the state again. We have a state transition probability. So what is the probability of Super Mario and all the enemies and everything that is in the environment of ending at a particular state at time t+1, given the current position of all these things, and given the action taken by the agent. Okay, the agent, this is going to be the computer behind to decide which button to press. Okay, right now this is unknown. Okay, we'll have to figure this out. And in reinforcement learning, the goal is what? Is to find what is the optimal policy. Okay, a policy here is going to be what is the action to take as a function of my state of the system. So as a function of where am I with respect to everything else in the game. Okay, so derive that optimal policy that will maximize the long-term expected utility as a function of what is the action taken and what is the state we're in. Okay, and the result of this is going to be somehow like this. So here is an example where we have a computer that has been programmed with reinforcement learning in order to play Super Mario. So here, none of these moves were actually programmed by a human. So no one told the computer how to play. Okay, here the algorithm learned how to play by trial and error. So playing for hundreds of thousands, if not millions of times, the Super Mario game to figure out as a function of where am I in the game with respect to the enemies, to the thing I can collect, what action should be taken. Okay? So you can find the link here to find that video on YouTube. So in the context of civil engineering, what can we do? Because our end goal is not to play Super Mario. Okay, we want to use that in real life engineering context. One of these applications could be for anomaly detection in the context of structural health monitoring. So here we have a representation of the Daniel Johnson Dam in Canada. This is an extremely large dam which has several hundreds of sensors onto it that will collect data according to what is this physical response to external solicitation. So here's an example of response over time. And what we want to do is that our environment here is going to be our SHM system, so the data collected by the system. And what we want to take as possible action is either to trigger or not trigger an alarm, to alert an engineers to say, come pay attention, there's something going on. Okay, we want to build an alarm triggering system using that reinforcement learning. So what is going to be the state of the system as a function of time? So it's going to be hidden states. Okay, this is, for instance, what we saw in module 7, when we saw how can we take a raw time series like this and break it down into subcomponents, representing, for instance, the local level, the local trend, the periodic phenomena, and all of this. Okay, if you don't remember this, go see module 7 for state-space model. So the hidden states we would extract with state-space model would become our state of the system. And then we have a reward as a function of the state and the action. Okay, as a function of, am I in a normal or abnormal condition? And do I trigger or not trigger an alarm? There's going to be a benefit for the infrastructure owner to have that early trigger of anomaly. So in that case, the reward is function of the state and the action taken. And again, what is the probability of transiting from a state and an action taken time t to a new state of time t+1? Right now, this is unknown. We'll have to figure that out. So reinforcement learning, still the same thing. Find the optimal policy that's going to maximize the long-term accumulation of reward, okay? The goal is not just to maximize the reward at time t. So it's always better to just do nothing. It's always less costly. But if I don't do anything now, it might influence my capacity to act later on. If I don't send an engineer right now, it might be too late later on, and I might have to deal with a bigger problem, which is going to cost a lot more. So we have here to figure out the optimal policy, taking into account not the short-term reward RT, the long-term accumulation of reward. Okay, it's that long-term planning we want to do with reinforcement learning. Other example level application, not all structures are instrumented with electronic sensors. Most of them still rely on visual inspection to monitor their condition. So there's an example of an inspector going and writing down what are going to be the defect, what are going to be the degradation sign of each structure. So here, if we have the timeline on the horizontal axis, here we have one inspection point, one visual inspection report for the structure number 002. So over time, every 2 to 4 years, each structure is inspected again and again. But we don't have this data for a single structure. We have it for an entire population of structure. Okay, and in addition to these visual inspection, we also know when intervention happens, such as maintenance or replacement of infrastructure. So using that large network scale database, what we can do is for an entire network across a city, a province, a country, we can use that database as our environment. Okay, this is going to be our infrastructure network. Then the possible action could be, for an example, wait, so means do nothing, let the structure degrade over time, repair or replace that structure. In the state here, the structure is going to be, for instance, what's in the inspection report. Typically, this is written down as percentage within categories, A being the best category, B, C, and D. Okay, this is what's typically used in North America. Then the reward of being in those states is function of the state itself. The probability of transition, just like before, it's unknown. We'll have to figure this one out. And reinforcement learning is the goal of maximizing the long-term expected utility. Okay, what does it mean? That this, for instance, if we would just try to maximize the reward at time t, the best thing to do would probably be to wait, because waiting costs nothing. So the best thing, if we just want to maximize our financial gain at time t, is just do nothing. But if I keep doing nothing, there's going to be a point, my infrastructure is going to be so bad that the cost for deferring the traffic somewhere else and the cost of repairing is going to definitely override all the costs I deferred by waiting. Okay, so the long-term best action to take is not to wait, even if the short-term action is to wait. Okay, so reinforcement learning is going to allow us to do that long-term planning. So even if my costs are going to be lower now to wait, I might have advantage of making preventive maintenance to avoid the high cost of replacement. Okay, this is what we're going to look at together. Other example of application, imagine we want to characterize a contaminated site. Okay, so the dashed boundary is the perimeter of the site I want to characterize. I want to know which part of the site is contaminated, which part is not. So the reality here is that these reddish region would be the contaminated part. Okay, but the thing is, up front, I don't know where these regions are. Okay, so how do I know where these regions are? By taking samples. Okay, I'm going to go with a drill. I'm going to take soil samples, send them to the lab. Each sample is going to cost me something. Okay, so what I want is the reinforcement learning to help me planning in that decision. Given the samples I've collected so far, where should I collect samples next? Okay, where's the next place I should move? Drill down in the soil, take soil sample, send it out to the lab. Okay, as a function of the sample already collected, where should I go next to collect more sample? In order not to minimize the volume of soil contaminated, but to minimize the number of samples I need to take, if I want to have the best or an exact knowledge or the best reasonable knowledge of what is the soil contamination characteristics of my region here. So here, my environment is going to be my contaminated site. My action are going to be to sample from a distance delta x and delta y from my current position, could be in meters, or stop. Okay, I've taken enough samples. My state would be for all the samples I have already taken, what would be the concentration, for instance, here in mercury? That could be the contaminant I expect here in my soil. The reward is function of the state I'm seeing, as well as the action already taken. My transition probability is unknown. I'll have to learn it from data. And again, reinforcement learning, maximize the long-term gain as we've seen before. Last example here, an example particularly problematic for Montreal. We have an infestation last year from the emerald ash borer insects. Okay, these are parasitic insects that comes and kill the ash trees in the city. Okay, so we need to derive an optimal tree cutting policy, okay, because our mitigation measure is to try to isolate the region where are infected to slow down the propagation to the other region in the city, okay. So here we have a map from the city of Montreal where all the dots would be the ash trees, okay. So our environment would be the tree population, okay. The action, what it would be, it's either to cut a tree or wait. But you can imagine that no one who has an ash tree on its property wanted to be cut. So if we would just be trying to maximize the short-term reward, we would just wait until the last minute to cut the tree. But if we wait too late, then the rate of propagation of that insect might just increase and cause more harm than by having done preventing cuts of the tree. So you can imagine that the short-term reward associated with cutting is going to be higher than by waiting, okay? But it doesn't mean that the long-term reward is. In that case, the state is function of all the insects recenses or the insect observed across the city. The reward is function of the state and actually the action as well. And the transition probability, as before, unknown. We need to learn it from data. Reinforcement learning, maximize the long-term expected utility for being in state, taking in action. Okay, so all of this can be seen under the umbrella of reinforcement learning. Okay, and in a simplified way, we can subdivide reinforcement learning into two main branches. Okay, the first one is when we can explicitly represent that conditional probability. Okay, when it can explicitly represent the conditional probability of being in a state at time t+1, given the current state in action. So in that case, we're in the branch of model-based reinforcement learning. Okay, this is what we're going to solve using MDP, Markov decision process, or POMDP, partially observable Markov decision process. This is what we're going to see a little bit later on. The second branch is when we cannot represent explicitly that conditional probability. In that case, these are going to be the model-free reinforcement learning methods, such as Q-learning, SARSA, etc. Okay, here we're not going to cover all this, but we're going to see the basic for MDP, POMDP, as well as Q-learning. So here it is for the introduction. So what we're going to see first is the nomenclature. How can we frame our problem of long-term accumulation of reward over time? Okay, we're going to see the nomenclature associated with it and the basic framing for a toy problem. Then we're going to see how we can solve that toy problem using first Markov decision process, which is a model-based reinforcement learning, and then how can we extend it to Q-learning, a model-free reinforcement learning method. So this is our last module which cover here that AI and sequential decision problem through reinforcement learning. Okay, so for the nomenclature, we're first going to look at all the definition of variable. What is really in a concrete term an environment, a reward, an agent, and all of this. Then we're going to see how can we frame all these quantity in a simple toy problem associated with infrastructure maintenance planning. Okay, so let's apply reinforcement learning to sequential decision problem. So here, for instance, the state, what are going to be? They can be either continuous quantity or discrete quantity. So S is going to be the variable used to describe our possible states, which can be either continuous in 1D or multiple dimension domain, or could be discrete, so belonging to a discrete set of possible categories. So in the context of this class, we're going to focus only on the discrete state space, which is simpler and easier to handle. But the basic core concept we're going to see transpose also to the continuous domain as well. Then we're going to have actions. So here we assume that our actions belong to a discrete set of possible actions. We're going to have our transition model. So that transition model describes the probability of landing in a state S prime, given that I'm currently in a state Sj, and I take an action AI. So here that probability is actually the probability for that state S prime being the kth state, so among the S possible states. Given that I'm currently in the jth state among all of my possible states, and I take the ith action among my possible action. Okay, and this is a probability mass function which describes this probability for all possible cases, so all possible state S prime from the state 1 up to S among all my next state here. The reward, so the reward is a generic function of the current state, the current action taken, and the next state that's going to happen next. So typically the reward is defined as a real number. Okay, and here we can have special cases which are equivalent. Sometimes the reward might only be a function of the current state and current action, so not function of the next state. This is fine. Sometimes the reward might only be a function of the state independent of the action. That is fine as well. Okay, you have to tailor this reward function for what are the specificities of your current problem. In terms of policy, so policy is the end goal of reinforcement learning or sequential decision planning. At the end, what you want is to define what is my policy. And a policy is a map between states and action. It means for each of the action from S1 to SS, what is the action to take? So when I'm in action S1, this is the action I take. When I'm in action S2, this is the action I take, okay? And pi denote that policy. For each of the state, what is the associated action? So let's frame this in the context of the infrastructure maintenance problem, okay? So let's say that the possible states go from 0% to 100%, okay? And these conditions are actually rating given by visual inspection that are done every 2 years, okay? So my states are from 0% to 100%. Then my data I would use here to build my model is going to be made of kind of time series of visual inspection. So in that case, we see an example for 20 years. What was the condition observed by inspector at every year or every 2 years, okay? So each point here represents the state that was observed by a visual inspection, okay? So my database for my first time series is a collection of T time step, okay? But I don't only have one time series, I can have a second one, I can have N time series, where you can see here that each time the structure over time degrade and transit starting in perfect condition, and as time goes, it goes to lower condition just because of the effect of degradation. Okay, now what are my possible actions? So my set of possible action here is going to be to either do nothing, maintain, or replace, okay? So here what we want to do, next what we want to look at is the model. So we spoke a lot of time about my transition model, and I say this is unknown, okay? So the goal here would be to use my data set we described previously in order to learn that conditional probability. And here that model is going to be special. It's going to be a Markovian model. So remember from the previous model we were seeing, the Markov hypothesis states that the future is independent of the past given the present, okay? So here we want to use that same Markov hypothesis to build our transition model. What does it mean? Is that transition probability for state t plus 1 that depends on all the states from at time 1 up to time t, it's equivalent to that transition probability that would only depend on time t, okay? So that Markovian hypothesis is going to greatly simplify the building of our transition model. So here what we can do, we can use, for instance, an MLE approximation. This is why I have a probability with this little hat on top to denote this is an approximation, this is an estimator. In this case, an MLE estimator for the conditional probability of ending at time t plus 1 in state k, given that it's at time t I was in state I, and I took the action of doing nothing. So in that case, how do I quantify that probability? I look at the relative number of instances in my database. the relative number of instances that I take this action, start in this action, and end up with, start with this action, be in that state, and end up in that state. So that translates into the number of instances in my database where I start in condition I end up in condition K, while, or divided by the number of instances where I started in the state I. So at the end, if we do that quantification using our database, we're gonna have a conditional probability such as this one, okay? So here, if we start the conditional probability for the action doing nothing, and we start with the state I equal 1. Okay, I start in state 1. So this is going to be the conditional probability of if the first line is going to be starting in state 1, and this is the probability of ending it in each state st plus 1. So this is the probability of ending in state t plus 1 equal 1, 2, 3, 4, 5, 6. Okay, we see that from the physics of the problem, if I start in state 1, which corresponds to 100%, there's a high probability that I'm going to remain at 100%. There's a small probability I'm going to end in state 2, a lower probability in state 3, and 0 probability that I'm going to go in a really bad state. I can do the same for state 2, and I do that for actually all of my states. And the result is a transition matrix a little bit like this, which tell me what is the conditional probability of starting in a state, these are the rows, ending in each of the other state at time t plus 1, these are the columns. And what you can see that we have in the gray region here, only zeros, okay? Because we see that for a state, say 3, there's a 0 probability that if my action is to do nothing, the state is gonna improve over time, okay? A structure only degrades and only gets towards the worst condition. So that's why my lower half here is 0, because without intervention, the structure condition cannot improve itself. Okay, but I don't only have one action doing nothing. I can also, as we defined earlier, we can maintain and we can replace the structure. So if I decide instead of doing nothing and let the degradation process go on, I could decide to maintain my structure. So in that case, I would have that deterministic transition probability. So before, I knew that if I let the degradation process, or I don't know exactly if I let my degradation process go on, what's going to be the next state, because this is intrinsically something that is stochastic. Whereas in the case of maintenance, we assume that the action is deterministic. Whereas we're going to be in one grade better than we were before. So in this case, if we were in the last possible state, so 0%, we assume that if we maintain, we're going to jump one state and be now in condition 1. If we're in condition 1, we're going to jump in condition 2. If we're in condition 2, 3, etc. And we assume that if we were already in condition 1, we're going to remain in condition 1 with probability 1. Okay, so everything, it's either 1 or 0, because here we assume that the action of maintaining is going to be deterministic, okay, leading to a sure outcome. Same thing for replacing, but with maintenance, we just jump one condition. With replacement, we go back to the 100%, go back to the first state, okay? So you can assume that all these actions are not going to have the same cost associated with it. So doing nothing is cheap. It costs nothing, okay? But then the structure might degrade over time. Maintaining is going to be cheaper than replacing, but also is associated with a lesser improvement in the condition. So let's look at that in a little more details by defining what are the rewards associated with what I defined here. Okay, what is the reward associated with being in a state S and for taking an action A? So for this specific problem, we can decouple both. So in this case, the reward associated with the state space is going to be defined by AADTF, the annual average daily traffic flow. If I multiply this, since it's a daily value, by 365 days per year, is going to be the annual average traffic flow, times what is the value per user for using, say, this bridge. Okay, this is not a toll booth fee that the user has to pay. This is the value for society to having that user using the bridge. So let's quantify this as something like $3 per user times what is the capacity of the structure to let the traffic flow, so the number of users per day using the structure, as a function of its state. So we're going to say that the capacity function of the state is that if the state is 100% up to 60%, 100% of the capacity can be used. Okay, so we can have the average daily traffic flow of user times 365 users per day. However, if the condition is 0, we cannot allow any user to go on the structure. The structure must be closed, so 0 traffic. And if the condition is 20% or 40%, we can see a sharp reduction into the amount of traffic we can let go on the structure. Okay, in that case, if we assume that we have 100,000 users per day, 100,000 users, so that means that the reward is going to be $109 million for the states 1 to 3. Then you see it drop and go to 0 for the last state. Then we have the reward for the actions. So the reward for doing nothing is 0. Okay, it costs 0 to do nothing. Then if we repair, it's going to cost $5 million to repair the structure, and it's going to cost me $20 million if I want to completely replace it. Okay, so we have a reward function for being in a state, and we have a reward function for taking actions. And here, the generic reward function we saw is function of the states, the action, and the next state. In our case, we can simplify this to the reward function of the current state and action. And in our case, it's simply an additive reward function for the state and for the action. Okay, so here, if we want to look at what are going to be the optimal action. Okay, so here if we say that given that the transition model is Markovian, so Markov hypothesis, the future is independent of the past given the present. The goal of MDP, a Markov decision process, is going to be to identify what are the optimal actions A that are to be taken for each state S. Okay, and this is defined by my policy. And here, when we talk about optimal action, pi is my policy. Pi star is going to be my optimal policy as a function of all my possible states F. Okay, so here in my optimal policy, what I'm going to have is what is the best action I can take A, given that I'm in state 1. Same thing for state 2 up to my last state. Okay, now let's jump into the core of our model-based reinforcement learning, Markov decision process. So first thing we need to do is to define what is our utility. Okay, what is the utility over time? And how do we factor that in to not only consider the reward at time t, but the sum of reward over a planning horizon. Then we're going to see how can we solve this problem of figuring out what is going to be my optimal policy using value iteration, policy iteration, and how can we finally extend this in cases that is fairly more complex of partially observable state. We're going to see that next. Okay, first thing to start with MDP, we need to define what is a planning horizon. Okay, there are two main choices. The first one is going to be a finite planning horizon. Okay, how long in the future I want to define my problem for. Okay, for instance, in the case of bridge maintenance, let's say I just want to plan for the course of the next 10 years, and after the next 10 years, I don't care what happened. Okay, this would be a finite planning horizon. So the reward and utility are going to be considered over a fixed period of time, say the scope of 10 years. But there's an issue with this. Okay, here, if you have a finite planning horizon, it means that intrinsically, in many cases, the optimal policy is going to end up being non-stationary. What does it mean? The optimal action to take as a function of the state you're in depends on the time. Where are you in your planning horizon? You can imagine, for instance, if you have a state that is in a really bad condition, so on the lower end, say at 20%, and you're in the first year of your planning horizon, most likely you'll want to replace that structure because it's so bad that you won't make it through the 10 years. On the other hand, imagine you're at 2 weeks to finishing your 10 years planning horizon, and you're in that 20% condition. it's unlikely that you'll want to replace the structure because you only have to stretch it for 2 more weeks. Okay, so this is the issue associated with finite planning horizon. It makes the policy non-stationary. The other end is if we consider infinite planning horizon. Okay, it's never stopped. So we never stop needing that bridge being open. Okay, no matter how far we project ourselves in the future, we'll always need that link being open. Okay, so there's never going to be a point in time where I say I don't need to manage that structure. So the good thing of this is that first, before looking at the good thing, it means that if we have an infinite planning horizon, we need to consider the reward and utilities over an infinite period of time. And the consequence of this is that now the optimal policy is stationary. What does it mean? If I don't consider there's going to be an end time when I'm not going to need that bridge anymore for my society, it means that if I'm in a 20% condition, either if I'm in a 20% condition right now, in 20 years from now, or in 100 years from now, the actual action to take, the optimal action to take, will remain the same. Okay? Because now is not different than the future. So in many contexts in civil engineering, the actual application of infinite planning horizon is well suited for the type of problem we're looking at. And on top of that, the advantage is it's much easier to handle. So in the context of this class, we're only going to focus ourselves on the infinite planning horizon for which the optimal policy is stationary. Okay, how do we define the utility for an infinite planning horizon? Because the utility at the end is going to be our metric of how good am I behaving over time while interacting with my environment. Okay, so the first thing we need to look at is we cannot only take the sum over an infinite planning horizon for an infinite amount of reward, okay? Because if we sum an infinite amount of positive reward over time, this sum is going to be infinity. So if I want to compare how good is one action versus the other action, where both utilities are going to be infinite, I won't be able to do it, okay? So if I want to be able to compare the value of two action, or in this case, the utility of two action, I need to consider not this infinite sum of reward, but the infinite sum of discounted reward over time. It means that I assign a greater values for events that are close in times from now than for things that are going to happen at a distant future from now, okay? So now we need to introduce the concept of a discount factor, which is between 0 and 1, excluding 1, okay? And the discounted sum of reward over an infinite planning horizon is finite. It means it will allow us to compare what is the utility for us of either choosing one action or the other. And note that you can conceptually relate the concept of a discount factor between 0 and 1 to an interest rate, where an interest rate would be 1 over gamma minus 1. Okay, you can go from a concept of interest rate or discount factor using this transformation. So here we define the utility for being in a state st at time 0, st at time 1, and up to st at time infinity. So being in all these different states over an infinite planning horizon as the discounted sum of all these rewards. So the reward for being in state s at time 0 plus gamma, my discount factor, times the reward of being in state s1 at time 1, and like this, gamma squared, gamma power 3, etc. And I do that infinite sum. So I sum from t equals 0 to infinity of gamma to the power t, the reward of being in a given state at time t. And here, the good thing is that this quantity is finite and is bounded by the maximal value of the reward among all possible state s, divided by 1 minus gamma, my discount factor. But here, the issue we have is that here, it assumes that we know what are going to be the states in the future. But actually, at this point in time, we don't know what are going to be the future state. We might know what is our current state at time 0, but we don't know what the future is going to be because we don't have a full control of what is our environment and what is going to be the next state. So the only thing we have access to in this case is the knowledge of our transition model, which is a conditional probability. Given that I know the state now, I don't know exactly what's going to be the next state. However, I can quantify the probability of each of those next states. Okay, so we have to transform this deterministic setup into a stochastic setup. Okay, given that I know my transition model is given my current state and the action taken, what is the probability of each next possible state? And given my knowledge of what is the reward function, we want to compute not the utility, but the expected utility over my infinite planning horizon. So that is expected utility. So the expectation of my utility for the state, for being in a state S and following a policy pi for my next state is going to be my current reward for being in a state S plus the expectation for the infinite sum of my discounted reward for my future planning horizon, where my current state S is currently known. However, my future states are not known. They're treated as random variable. That's why we take the expectations. Okay, I know the current state I'm in, and I want to factor in that I don't know exactly what are going to be my future state. That's why I consider here that expected value. And this is the long form, the expected utility. But in the short form, we're going to represent by U with a line over U for the expected utility of being in a state S and following a policy P for my future state. Okay, so what is it? Keep in mind the difference. RFS is the short-term reward, the immediate reward for being in a state. But here what I want to maximize is not R of S, is U of S. Okay, given that I'm in a given state, how useful is it for me to be in that state? Not for time t, but for the whole infinite planning horizon. That takes into account that future states are heavily discounted in comparison with the nearby states or the nearby time steps. And implicitly, it's going to often happen that we're going to not represent that policy pi, even it's always implicit there. Okay, so an expected utility, since we don't know what are going to be in the next state, it's always required defining the action we're going to take. And these actions are defined according to our policy pi, whether we represent it explicitly or in this case implicitly. So all these trees are equivalent formulation of or representation of the same thing. And the end goal is to obtain that optimal policy. So pi is my policy, pi star is going to be my optimal policy that define for each state S what's the optimal action to take. So in this case, that optimal action is going to be the argument A, the action, that's going to maximize the quantity here. So the quantity is going to be the sum over all the possible state of the product of the conditional probability for the corresponding next state, conditional on the action I'm taking and the state I'm currently in, times the reward for being in a state, taking an action, and landing in a new state S prime, plus gamma, my discount factor, times the expected utility for the next state, okay? Given that I'm following for that expected utility, my optimal policy. But here, I don't know if you noticed, but we have a problem, okay? Because we say that in order to define the optimal policy, I must know the optimal policy, okay? So this is the problem because we have the optimal policy on both sides of the equality. So it means in order to solve this relation, we'll need to use iterative resolution. Okay, so now the core, the fundamental core of that utility function and of planning is defined by the Bellman equation. Okay, in words, the Bellman equation says that the utility of a state is going to be the immediate reward for that state plus the expected discounted utility of the next state, given that we've taken the optimal action. Okay, this is exactly what we framed in the previous equation. In words, this is how we describe that Bellman equation. And the Bellman equation is the following. Okay, we're going to define the expected utility for a state S as being the max over all possible action we can take of the sum over all possible next state S prime of the conditional probability for all of these state S prime given the current condition, the current state and the current action taken times the reward for state action and next state S prime plus gamma times the expected utility of that next state S prime. Okay, this is the Bellman equation. And now the Bellman update or the value iteration step is going to be how can we solve recursively that expected utility? How can we evaluate that expected utility if it appears on both sides of the equality? So that left arrow represents we update that quantity from what we have on the right hand side. It also depends on that quantity. So now we have a superscript. Okay, that superscript represents we have an iterative process. Okay, we start from our knowledge at time I and we update that same knowledge at iteration I plus 1. Okay, now it's the same thing as the Bellman equation I initially described, but now in an update setup where I use my current knowledge for the expected utility for state S prime to update my expected utility for state S at iteration I plus 1. Okay, so we're gonna look into detail how can we do that value iteration step in order to recursively update our expected utility U bar. Okay, first thing in the value iteration is going to be to define a bunch of things, such as what are our possible states, what are our possible actions, what is going to be our transition model, what is going to be our reward function, what is going to be our discount factor, and we're going to need to define a tolerance, convergent tolerance. Then first thing, we're going to initialize our expected utility. Okay, so the expected utility for all states is going to be 0. So expected utility or expected utility prime, U bar and U bar prime are going to be the same thing. It's only that these are for 2 consecutive iterations. So this is like I and I plus 1. Okay, so while either my expected utility are 0, this is my starting point, or if the difference between my expected utility is greater than my convergence tolerance, keep doing my while loop. So in this case, I'm going to say that my expected utility U prime is going to be overriding my current expected utility U bar. Then what I'm going to do, I'm going to start a loop for each possible state in S. Okay. Then I'm going to do a second loop for all possible action in A. Then what I'm going to do, I'm going to calculate what is my expected utility for each possible S for each possible A, where as defined by the Bellman equation, my expected utility is going to be the sum over all state S prime, my probability for that landing in that state S prime as a function of S and A, which are in my loop here, times the reward of SA and S prime plus discount factor times my current knowledge of the expected utility U bar of S prime. Okay, once I've done this for all action, I can update what is my optimal policy, because the optimal policy is going to simply be the action that maximizes what I would have computed here. Okay, this is going to be my optimal action that goes into my policy associated with each state S. Then I can also update what is going to be my expected utility at iteration I plus 1, described by U prime. So it's going to be simply the expected utility that I've obtained here, but evaluated for my optimal action A prime. Okay, then I just loop this until I satisfy my convergence criteria. And at the end, I return my final expected utility and my final optimal policy. Okay, this is the value iteration algorithm that we can use to evaluate in a sequential context what is going to be my expected utilities. So let's apply this to our infrastructure maintenance problem. Okay, Little summary of what we defined earlier. We have the states from 100% to 0%. We have 6 possible states. The action is to do nothing, maintenance, or replace. We have a reward as a function of the state. We have a reward as a function of the action. So higher reward for better state, lower reward for lower state. Doing nothing is cheap, replacing is expensive, maintenance is in between. My reward for state and action is the sum of these two. And I have these conditional probability for doing nothing, maintaining, or replacing that we've defined together earlier. Okay, so now we're gonna use these information. We have everything in hand to apply our value iteration problem. So I'm gonna start by initializing what is my expected utility. Okay, I'm gonna assume for all state, it's $0 million. Okay, this is a naive initialization. Okay, this is a worst case scenario. So in this case, I'm gonna say, okay, after my first value iteration loop, what are my new utilities? I'm gonna go from 0 to something. Okay, and to do this, we use that Bellman update, which is the max over all the possible action for my 3 possible case. So here I have the action of doing nothing, maintain, replace, and I'm going to take the max of these 3 outcomes. So if I do it, for instance, I started from 0, and now this is my expected utility for after iteration 1. So we see that these values got updated. And here, keep in mind, if you try to redo manually the calculation, here I rounded off the values to simplify the visualization. But here, what you see as $110 million, the real thing is $109.5 million. I just rounded off these quantities. And then if I go from this 223 at iteration 1, if I go at value iteration 2, if I apply value iteration for a second times, so this is that superscript we have here, I go from 109.5 to 223, what I have here at the second iteration. And if I keep going, I'm gonna obtain result like this. So here, this is my reward function for being in a state. This is my reward function for taking an action. And these are my expected utility as a function of my value iteration loops. So I started with this at everything would be 0. And the first column is going to be for state 100%, the last state 0%. Okay? And then this is the evolution for 537 value iteration loops. So we start from 0, we go to 110, 110 to 223, etc. Okay? So here we're going to reproduce this step of going from the expected utility of being in state 1 at the first value iteration loop. The number we had was $109.5 million. How do we get to that $223 million for my second value iteration loop? Okay, so this is what we want to obtain. So the outcome of this is $223 million. Okay, mathematically is going to be and here we only look for the state s equal 1. So the reward for being in state 1 plus the maximum among all possible action of the sum among all possible future state, the conditional probability of landing on that state, the reward for the action plus gamma, my discount factor, times the expected utility for that next state. So in this case, we're going to explicitly do the calculation for all possible action to then take the max, okay? My first action, here's my conditional probability, okay, that we defined together earlier. So this defines actually the probability that if I'm in state 1, in this case, I'm considering that for being in state 1, okay? So I'm only looking at the first line in that matrix, okay? So I have 3 terms, the other ones are 0. So here, I'm gonna represent that sum over S prime. I have a non-zero probability only for these 3 states. So it's gonna be the probability 0.95 times my discount factor, 0.97 times $110 million. $110 million is going to be the expected utility at the previous value iteration loop, plus 3%, and the cost associated with the reward here is 0, so I have nothing. Plus, I have if I'm in state 1, I have a 3% chance of landing in state 1. If I'm in state 1, I have a 3% chance of landing in state 2, times discount factor, plus what was the expected utility of being in state 2? $211 million. Plus 0.02 times 0.97 times $309 million. The outcome is going to be $113 million. So this was if I was in state one and So this in the first line is what is the probability if I'm in state one of landing in state one, probability of landing in state two, probability of landing in state three. Okay, this is if I do nothing. So in this case, I don't have to add any reward for any of those cases because in all cases considering I'm not going to take any action. Then I'm going to consider the same quantity, but for my second action, which is repair. So it's going to be repair if I'm in state one. My outcome is deterministic. It's going to be if I'm in state one, for sure, I'm going to remain in state one, even if I repair. So in that case, it's going to be a certainty, so probability of 1 times my reward for repairing, minus $5 million, plus my discount factor times the expected utility of ending up in state 1, $110 million. So the result, $101.7 million. State 3, I have my third transition probability. If I'm in state 1, I'm for sure going to stay in state 1, probability 1. The cost, minus $20 million, plus 0.97 discount factor times, I'm going to end up in state 1, 110. 86.5. So here I have to take the action that's going to maximize these three. So the action that's going to maximize these three is going to be the first action, doing nothing, with an expected value of $113.5 million. So my updated expected utility is going to be the sum of that reward for being in state 1 plus the expected value. So the result, $223 million. This is what I have here. This is what I have here. Now I do it only for state 1, but keep in mind you would have to repeat this for each of the state in your state space. And now here my optimal policy, what is it? Is going to be to do nothing because I found that here the action that maximize is the first action. So it means that for now, whenever my state is 1, the best action I think I should take is do nothing. Okay. If we keep doing this over multiple iteration, you see that we start for each state with an expected value of 0. And as the number of iterations increase, we see that each of them asymptotically tends to their fixed values. So in that case, these are the expected utilities that we obtain at the end. And this is the associated optimal policy. Okay, so just by looking at this Bellman equation, by looking at this value iteration, we can derive that without human intervention, besides framing the problem, that it figured out on its own that if the state is 100%, the best one, the best action to do is just do nothing. If the state is either 80 or 80 up to 40%, the best thing is to maintain. And if the state is either 20 or 0%, you're better off just replacing it. It's not even worth maintaining. Okay? So we didn't explicitly tell them to do this. It figured it out on its own. Okay, so this is for the Bellman update and the value iteration, but there's an issue here. If the number of possible action A is large, one of the issues is that max operation, because we're going to need to repeat this a large number of times, and that can be computationally expensive. So the solution to this is to do policy iteration. So with policy iteration, what we're going to do is that instead of doing that max operation, we're going to choose the action to take by simply following our current policy pi. Okay? So in that case, this was value iteration. With policy iteration, we don't have that max anymore. That requires us to make multiple calculations in parallel. Instead, what we're going to do is that we're directly going to follow our action that is defined by our current optimal policy. Okay, this is what we do with policy iteration. So if we look at the algorithm, so we still have to define exactly the same thing as we had before for the value iteration. We initialize our expected value, we initialize our policy, okay? You can initialize it to whatever you want. Then we say that as long as my policy pi and pi prime, so pi and pi prime, you can see this as the policy at iteration I and policy at iteration I plus 1. okay? As long as in between two iterations, the policy are not the same, keep doing that while loop. So right now we assume that we're going to define them as being equal. Then we're going to do a loop of what we call policy evaluation. So policy evaluation is the same thing as value iteration, except that instead of doing the max among all possible action, what we're going to do is just take the action corresponding to the current policy pi of the state, okay? Then once we've done this, for each state in my state space, we're going to update our policy, okay? In order to update the policy, we're going to use our output from the policy evaluation, and we're going to take the action that maximizes the quantity here, the sum over all the future state S prime of the conditional probability of landing in that state S prime times the reward for a state, being in a state S, taking an action A, and landing in the next state S prime, plus gamma, my discount factor, times U bar, so my expected value for being in the next state S prime. And at the end, I'm going to keep doing this until in between two successive iterations, the updated policy remain the same. Once the two successive policy remain the same, it means that I won't see any change in my expected utility. So then I can return my final expected utility. So we're going to apply now the same, we're going to use policy iteration and apply it to the same problem we had before. So now we start by assuming my initial policy is going to be 1, 1, 1, 1, 1, 1, meaning no matter what is the state, I'm going to decide to do nothing because the first action is do nothing. If I calculate that expected utility, these would be the expected utility for doing nothing. Then what I'm going to do, I'm going to use this to update my new policy, okay, by finding the action that maximizes these three quantities. And I'm going to say that now my updated policy is going to be this one, okay? Instead of being 1, 1, 1, it's going to be 2, 2, 3, 3, 3, 3, meaning replace and maintain and replace. And this, in fact, modify my expected utilities. And I'm going to keep doing this, iteration 3 up to iteration 6. And what I've seen is that in between my 5th and my 6th iteration, the policy hasn't changed. Okay, the policy remained fixed, meaning that my first action was to 1, do nothing, then for the 3 subsequent state, maintain, and the last 2, replace. So in that case, meaning if I don't have change in the policy, I won't have any change in the expected utilities. So if we look in more detail, how do we go from the expected utility at the first policy iteration to the expected utility at the second iteration? Okay, so it's going from that $263 million to $3,483 million. So after my first policy iteration loop, these were the result I obtained, and this was my current optimal policy. Okay, now we're going to look specifically for updating the state 1. Okay, so it means that my current optimal policy, if I'm in state 1, is to do action 2, which is replacing. So in that case, I'm going to look at here my policy evaluation loop. So in my policy evaluation loop, I need 2 subscript, or actually 3 subscript. This is the expected utility for state 1. Okay, the first subscript is going to be the policy iteration loop, what we see here. And the second subscript is going to be the policy evaluation loop, because in the algorithm we saw together, remember there are 2 for loops. And this is the calculation we're doing. Okay, here now the policy is the second policy, replace. So replace, keep in mind from what we defined earlier, it was a deterministic policy, meaning I'm certain I'm going to remain in state 1, for which the utility is the reward of being in state 1 is $109.5 million minus the reward associated with the action of maintaining is $5 million plus 0.97 times my current expected utility, $2,063 million. Okay, this gives me my new updated value for my policy evaluation loop for the expected utility of being in state 1. Then I'm going to repeat that calculation, but use that value here as expected utility. I'm going to obtain a new updated value, and I'm going to keep doing this. In this case, for over 350 iteration, you see that my expected utility is $3,483 million versus $3,483. So it's the same value. And if I keep at 351, still the same value. I've converged to a steady state for my expected value. And so this is how I go from that 2063 to that $3,483 million from policy iteration 1 to iteration 2. Okay. So in that case, once I've completed one loop of policy evaluation, what I'm going to do, I'm going to update my policy, okay? From going to policy at iteration 1 to policy at iteration 2. So my initial policy was to maintain, okay? Now, if I want to see it's still my optimal policy, I need to calculate the argument that's going to maximize these quantities here. So this is my reward for being in state 1 plus the reward for taking the action 1, do nothing. So this is going to be 0 plus discount factor times the probability for each possible next state, state 1, 2, 3, for action doing nothing, times the expected utility of ending up in each of those states. So this is the probability of the expected value I have here, this is the expected value I have here, and the third one is the case I have here, okay? The result is $3,488 million. I do the same thing for the action of maintaining. So in that case, the expected reward, the reward for being in state 1, minus the reward for taking the action of maintaining, discount factor, the deterministic probability, so 1 of ending in state 1, times its expected utility defined here. So $3,483 million, same thing for replacement. And I can see that here, the best action is 1, do nothing. Okay, so I went from an optimal action at iteration 1 of maintaining to an optimal action at iteration 2 of directly do nothing. So if we continue until we converge, we're going to see that the optimal policy we find is exactly the same as what we had before. And we can represent this as a function of the states here and the action. The height represents the expected utility for each action. And if instead of representing directly the expected utility, we can scale them down as the relative expected utility compared to the worst possible action we can do to better distinguish between them. So in that case, we can see that for the first two state, or for the first state, so 100%, the highest expected utility among the three action is to do nothing. For the next three state, the highest expected utility is for maintaining, and for the last two state, the highest expected utility is for replacing. This is how we define our optimal policy. So keep in mind here, as we've seen together, whether you choose policy evaluation or policy iteration or value iteration, both will lead to the same expected value and as a consequence to the same policy. But in practice, typically policy iteration is going to be faster than value iteration. Now, one thing we brush off and we didn't consider is that in many cases, actually, you won't even know exactly what state S you're in. Okay, it might be that you can have an imperfect observation of the current state you're in. So in that case, for MDP, we need to know the state S we're currently in. And if it's not the case, what we can use is POMDP. Okay, in that case, it's going to be partially observable Markov decision process. So we're not going to review it in detail, but I want you to keep in mind that this is a much more complex problem. Okay, so if ever you want to do this, in most like real life interesting cases, this is a problem that's exactly intractable. So it means that you won't necessarily have an exact solution to solve it. So the end result is going to be computationally a lot more demanding. So if you want to see more detail about this, I recommend chapter 17 from Russell and Norvig, where you can get all the detail from that POMDP. For now, together, I just want you to keep in mind that with MDP, you need to know exactly the state you're in. Otherwise, you're going to be in a context in the POMDP, which is computationally a lot more challenging to tackle. Okay, so far what we've seen is the model-based branch of, or at least we've seen a part of the model-based branch of reinforcement learning. Okay, so we saw that when we can explicitly represent that conditional probability, we would be using MDP or POMDP, which are the model-based reinforcement learning. This is not the whole thing of model-based reinforcement learning, but the foundation of model-based reinforcement learning. For cases where we don't have access to that explicit representation of conditional probability, this is where we're going to use that model-free reinforcement learning. So we're going to use what is known as Q-learning or Sarsa-method. There are a bunch of others, but here we're going to restrict ourselves specifically to Q-learning, okay? Which will allow us to define what is going to be our optimal policy for cases where we don't have access to that conditional probability. Okay, for instance, in the case of the Super Mario problem, the problem it's not suited for first discrete representation of the state, and the number of state might be so great that we cannot explicitly represent that conditional probability in a form of a table. So what we want to do with Q-learning, or more generally with model-free reinforcement learning, is to learn what is going to be our optimal policy by letting the agent, meaning our agent in this case here is going to be the computer that define what are the action to take, with the environment, okay? The agent is what decides what action to take and perceive the reward, perceive the environment, and this interaction is going to go with the environment. So we want the interaction between the agent and environment to operate over multiple episodes. So here in the episode, you can see this as in a case where it would be one play by the computer of Super Mario. Okay, you give the controller to the computer and you let it play. Okay, at the beginning it's going to play really bad, but as it plays more and more and more games, or more and more episodes, it's going to become better and better at playing. Okay, so rather than having access to that conditional probability, now we want to learn how to behave by playing over episodes, okay, as data come in. So in this case, for Q-learning, what we're going to see first, the context of Q-learning, this is what we've just covered. Then we're going to frame this problem, this model-free learning problem, as temporal difference learning. Then we're going to look at specifically the Q-learning algorithm, and we're going to apply it to see how could we retrieve the same result as we had before through the infrastructure maintenance problem. And finally, we're going to see how can we extend to more challenging, more interesting problem using function approximation. Okay, so a quick reminder, we define the whole performance metric we're trying to maximize as the expected utility. And here we define the utility in the case of an infinite planning horizon as the sum of discounted reward. So explicitly, we said that the utility for being in a state S and following a state policy pi for the next state as the sum from t equals 0 to infinity of gamma to the power t times the reward for being in a state, taking an action, and ending up in a state t plus 1. Okay, where the action taken at each time t is defined by our policy, which is a function itself of the state we're currently in. Then we define since we don't know what are the future state we're going to be in, we define a concept of expected utility. So we can either represent the expected utility like this, or in a shorter form by u with a line on top of it. And we can express explicitly the dependence on the policy pi or not. So all of these are equivalent representation, but in all cases, we're always talking about the expected utility. And here, what we did previously is that we evaluate that expected utility using the knowledge of that conditional probability of ending up in the state, given the state in the action we're currently in. In this case, we're going to take a different path, okay? We're going to say that, okay, actually, I might be able to approximate that expected utility, not using the Bellman update equation we've seen earlier, but by instead taking the average utility for several realization in a episode, okay? So instead of going with that Bellman equation update, what we're going to say is that we're going to try to average the utility as we observe them by interacting with the environment. Okay, and to see how it works, we're going to take a little tangent line in order to dig a little more. How do we calculate a running average? Okay, so let's take a generic example where we have a set here of t realization for a random variable. Okay, so we have a set that contains hundreds of instances, and what we want to look at is what is going to be the average of that set. So the sum of all the elements divided by the number of elements in the set. Okay, so this is if I have access to the whole set at once. But if I don't have access to that whole set at once, but I receive the item one by one, what I could do is calculate a running average as data come in. And the formula to calculate that running average is that the running average at time t is equal to the running average at time t minus 1 plus 1 over t times the current value I'm observing minus the expected value at time t minus 1. Okay, this is the formulation to calculate a running average as data come in. So if we apply this to an example where we have a set of 500 realization of a normal random variable with expected value 3 and variance 1. So here we know by definition that the average should get really close to 3 because it's the expected value. So if we look at the result we would obtain, so if we take the entire set of 500 realization, the empirical average is going to be given by that red dashed line, which is very close to 3. Okay? But then if instead of using that whole set, we would use that formulation that allows us to do the running average in order to, as with the first data point, and as I collect more and more data, I can see that I have fluctuation in the value of the running average, but I asymptotically tends to the correct value obtained using the entire set. Okay, and this is the core principle we want to use here with temporal difference learning. Okay, so this is our formula for the running average in the generic form. This is how we can apply it to calculate the expected utility as I'm going to perceive the utility as I'm going through an episode while the agent interacts with the environment. Okay, so this is my expected value at iteration I plus 1. Is going to be updated by the expected value at iteration I for being in state S plus 1 over the number of time I've seen that specific time S. So this is equivalent to the 1 over t times the utility of perceiving the state S minus the expected utility of perceiving that state S. So in that case, in TD learning, it's defined by this equation. Okay, TD for temporal difference learning. My updated at iteration I plus 1 expected utility is going to be updated by the expected utility at iteration I plus alpha. Okay, alpha is a proxy for the number of time we've seen a specific state, or 1 over that ratio, times the TD target. So TD target here is really analogous to what we've seen earlier when we defined the concept of expected utility and optimal policy. So here that formulation we see here is exactly the same formulation we're currently seeing here. Okay, this is defined as my TD target, my current perceived utility. Okay, it's going to be the reward for being in a state, taking an action, and ending in a state S prime plus gamma, my discount factor, times the expected utility for my next state minus my here current utility at step high for being in that state. Okay, the difference between my current perceived utility and my previous knowledge of that utility is going to be a correction factor for what's my current factor, my current knowledge of the current utility. Okay, and as time is going to increase, alpha is going to reduce to 0. So less and less I'm going to correct my current knowledge with that quantity here. So here, alpha is what we call the learning rate. And that learning rate must satisfy two properties. So first, the sum from n equal 1 to infinity for that alpha value that depends on the number of times I've seen a state and taken an action must be equal to infinity. And the sum of the square must be smaller than infinity. And there are many cases we can use that satisfy this property. A generic simple formulation is to say that my alpha, my learning rate, is going to be a function of the number of times I've seen a state and I've seen an action. Is going to be the ratio of C divided by C plus that number of times, where C is simply a positive constant. So if we take that simple formulation for that learning rate, we're going to satisfy these two criteria. So we call it Q learning because actually we replace our expected utility by what is called an action utility function, denoted by Q, okay? That action utility function is a function of a state and an action, okay? So here there's a one-to-one relationship between the Q function and my expected utility, okay? If I take the action A that maximizes this function, it's gonna return the expected utility for following my optimal policy, okay? Same as before. So now with the action utility function Q, I simply explicitly represent the dependency of my expected utility on the possible action A. Okay, and this analogously, if I take my Q function and look at which action maximizes it, this is going to be my optimal action defining my policy. So the general equation for temporal difference Q learning, often simply referred as Q learning, is going to be an, again, recursive updating equation. So my updated Q values at iteration I+1 for a given state in action is going to be updated through my current knowledge for the Q value for a state in action, plus alpha, my learning rate, times the reward function, plus my discount factor, times the maximal value for my Q function for the next state and next action, minus my current value for my Q function. And here, Q learning is intrinsically an off-policy learning method. Why? Because here, in that updating equation, we don't use the policy anywhere, okay? Instead of taking the next action that's gonna follow the policy, we're gonna always take the action that's gonna maximize my Q function for the next state, okay? So here, it's an off-policy method because we're always gonna take the best possible next action. Method that we're not going to cover here, but if you're interested, go see in the literature. SARSA is going to be an on-policy learning because instead of using the max here, we're going to follow actually the next state that is defined by the current optimal policy. Okay, one more thing we need to see before applying this is that we have a trade-off between exploring new possible action and exploiting our knowledge of what's the current optimal policy. Okay, so when we're gonna when our agent is gonna interact with the environment, for instance, playing Super Mario, okay, as it's gonna evolve through space, so evolve from a state S to a state S prime, we cannot always let the agent decide to play according what is its current knowledge of the optimal policy. Why? Because this would lead to a local maximum. Initially, we'll have a really poor knowledge of what's the optimal policy. So it means that if we always tell the agent play according to that policy, you're always going to stuck at the suboptimal performance, okay? Because our current knowledge of policy is really poor. On the other hand, we cannot let the agent always act randomly, because this is not going to work neither, because it's going to lead to a poor performance. An agent, a player that would play Super Mario randomly is never going to cheat anything. So we have a poor initial knowledge of the policy. We cannot rely on the policy. We cannot act randomly neither. So one solution among many other to solve this exploitation trade-off is, in a simple format, is what we call an epsilon Grady agent, okay? In few words, an epsilon Grady agent is going to play or is going to act randomly with probability epsilon and is going to follow the currently optimal policy with probability 1 minus epsilon, okay? Mathematically, we're going to say that at each time, the action taken is going to be a random action with probability epsilon, which can be a function of the number of times we've seen that current state. And with probability 1 minus epsilon, with probability 1 minus epsilon, what we're going to do is take an action. Okay, here it's not 1 minus probability of epsilon, it's probability of 1 minus epsilon. So here there's a little typo. So it's not the probability of epsilon, it's probability equals to epsilon. Same here as the probability equals to 1 minus epsilon. So there's a typo here I'm going to correct. So with probability 1 minus epsilon is going to take a greedy action, which means it's going to take the action that's going to maximize my current action value function. Okay? And in this case, my epsilon and my probability of a random action is function of how many times I've seen a specific state. And that epsilon should tend to 0 as the number of times I've seen a given action, a given state, tends to infinity. So at the beginning, I will tend to play a lot randomly because my policy is really bad. But as time will go, I will less and less play randomly and more follow what my policy is telling me. So if we summarize or if we detail all the steps in the algorithm for the temporal difference Q-learning, or short word for Q-learning, we define what are our possible state, possible action, reward function, what is our discount factor, what is the epsilon. It's going to be an epsilon function in order to do our epsilon greedy exploration, and alpha, my learning rate. I start by initializing my action value function Q at any value. A really conservative way is to initialize it to 0. Another more efficient way is often to initialize it at the maximal reward we have defined. That is not the maximal reward that is possible. We initialize the number of times we've seen a given state in action. We initialize it as 0 for all state and all actions. And we start our index here, I equals 0. So I start a first loop for a set of E episode. Okay, for each episode, I start by initializing my state. Okay, my Super Mario started in a given position. Then for each time in that episode, I'm going to interact with the environment. Okay, so here, the first step I'm going to do, I'm going to draw a random sample from a uniform distribution. Okay, and if that random sample is lesser than epsilon, my probability for a random action, I'm going to take a random action. If U is greater than epsilon, I'm going to take a greedy action, meaning I'm going to take my action that maximize my current action value function. Then once I decide what's going to be my action, I observe what is going to be both my reward and my next state. Okay, so this is a return by the actual environment. Then I do my update of my action value function using that TD learning update, where here I'm going to choose my Q function here, or my Q value for the action here, which lead to the maximal value for that Q value. So here I reassign my current state as being my next state as prime. I increment my value for the number of times I've seen a state in an action by +1. I increment my counter I by +1, so my iteration loop. And at the end, when I finish going through all my episodes, I'm going to return what is going to be the max of my Q function with respect to all possible action. This is going to be my expected utility for each state. And I'm going to obtain my optimal policy as the action that maximizes my action value function. Okay? So now we're going to apply this Q learning to the infrastructure maintenance problem. So here, keep in mind, in the infrastructure maintenance problem, we don't really need Q learning because we already have access to that transition probability. But what I want to look at with you is how applying that Q learning to the same problem would lead to the exact same expected utility as well as the same policy. Then if you need to apply it to a more complex problem where you don't have access to that conditional probability, you have confidence into what are the capacity and limitation of the application, the algorithm. So first, if we want to apply it to the infrastructure maintenance, we need to define what is going to be our learning rate. So here we're going to assume that the learning rate is a function of the number of times we've seen a state in action is going to be 70 divided by 70 plus this number of time n. Then my epsilon greedy function, which is function simply on the number of time I've seen a state, is going to be again 70 over 70 plus number of time I've seen the state. I initialize my action value function to 0 for all states for all actions. And my environment, in the case of Super Mario, my environment was the game itself that the computer would have played. In this case, I don't have access to that game, or the game is not played on the console. That game is all contained in my transition probability. So in this case, I have a conditional probability that I defined earlier for the action doing nothing, maintaining, or replacing. Okay? So here, what I'm going to do for that infrastructure maintenance problem, I'm going to play for a set of 500 episodes, so 500 bridge degradation time series, each comprising 100 steps. Okay? And if we apply the Q-learning algorithm we've seen together, we see first the epsilon, the exploitation trade-off, or the probability of each, the exploration or exploitation. At the beginning, epsilon is close to 1, meaning we're always going to act randomly. Okay, and as the number of episodes increase, we see that epsilon tends to 0. Okay, where the different lines represent different states, okay, from 0 to 100. And here we have the expected utility, which start at 0 and converge to values here that are exactly the same as what we've obtained before, either with value iteration or policy iteration. Okay, so we have both the same expected utility as well as the same policy. So here we confirm that whether we use policy iteration, value iteration, or expected utilities, they're both solving the same problem. Value iteration, policy iteration, where when you have access to the conditional probability for the transition probability, and we're going to use model-free methods such as Q-learning when we don't have access and we need the agent to interact with the environment in order to learn what is the optimal policy. So at the end, if we want to solve a problem, as we've seen earlier, of letting the computer learn how to play a game such as Super Mario, it's intrinsically something that is not well suited to be solved in a discrete environment as we've seen. So in such a case, what we need to do is to do Q-learning with function approximation. So in that case, the actions are the same as before, the controller, the button we can push. The state is as before. It's going to be a continuous state of where Super Mario with respect to all the components of its environment. Reward function of the state. But here, it's intrinsically unsuited to model a conditional probability. So the state space is going to be so large, it's already unmanageable, and it's just intrinsically not suited for this. So instead, what we're going to do is that we're directly going to represent our expected utility by an action value function and use Q-learning. But in this case, in the discrete environment we were looking at together, the Q of S and A is kind of a big table for all possible state, all possible action. But in this case, since we're in a continuous environment, it's not anymore a table. It's going to be a regression method, such as, for instance, a neural network. And now the task with Q-learning with function approximation would be to learn what are the bias and weights for all my parameters in my neural network in order to maximize my expected utility. So if you want more detail about these more advanced methods, I recommend that you go in chapter 21 from Russell and Norvig, or go in the detail in the book of Sutton and Bartow. So I'm going to wrap up by just summarizing what we've covered together. So first, as a general picture, what is AI? It's going to be a reproduction of an intelligent behavior by a machine. And a machine, keep in mind, it's not a physical machine, can be as simple as a computer. So the key is to perceive and interact with the environment in order to take sequential decision that's going to maximize the long-term expected utility. So in terms of nomenclature, we have state. So states can be either continuous or discrete. Here we focus mainly on discrete, but we can extend everything we saw to continuous environment. We have actions. So actions are, in our case, are always going to be discrete. We have a model of our environment. So given our current state in action, what is the probability of ending in a next state? We have the reward that tell us at an instant t, what is the reward we perceive for being in a state, taking an action, and ending in a state S prime. The policy is the end goal we're trying to reach. The policy is going to be a map between the current state we're in and what is going to be the action we should be taking. Okay, for each state, there's going to be an associated action. Then in a case where we can explicitly represent that conditional probability, that model of the environment, we can use model-based reinforcement learning through MDP, POMDP. Okay, these are not the only model-based methods, but the simplest one, which are the core of the field. Then if we cannot do that explicit representation, we can use model-free reinforcement learning. We've saw in detail the representation of Q-learning, which is going to be an off-policy algorithm because we're not following the policy when doing the update. We've considered infinite planning horizon because the reward and utilities are considered without time limit. And in this case, the key feature of an infinite planning horizon is that it's going to have a stationary policy, meaning that the policy is valid no matter when we are in time. This wouldn't be true if we were dealing with a finite planning horizon. So the key aspect of all the formulation we did, either with value, policy, or Q-learning, so value iteration, policy iteration, or Q-learning, is the Bellman equation. So it says the utility of a state is the immediate reward for that state, plus the expected discount utility for the next state, given that the optimal action is taken. Okay, this is summarizes what is here known as the Bellman equation. So the Bellman equation, the problem is that the expected utility appear on both sides of the equality. So the key to solve this is to use a recursive iterative process. Okay, so here we have the value iteration where we update at iteration i+1 or expected utility for our knowledge of the expected utility at time I or at iteration I. We can do the same thing with policy iteration. The difference between value and policy iteration is that with policy iteration, we don't have that max anymore, okay? Because instead of trying explicitly to use the action that maximizes this quantity here, we're just gonna follow the action as defined in our currently optimal policy. And this, in general, when the action space is large, is gonna save us potentially a lot of time. But in any case, once they've converged, the policy obtained using policy iteration or value iteration would be equivalent. Same thing for the expected utilities. But in general, with large action space, we're going to end up converging faster with policy than with value iteration. And finally, when we don't have access to that conditional probability, so the model of the environment, we're going to learn as our agent explore the environment. So in that case, we use the TD, temporal difference Q-learning, or simply Q-learning, where in this case, we said earlier, this is an off-policy algorithm, because here we're going to update not using the policy, but using the action that maximize our action value function. So if you want more detail for the advanced method, go see either Sutton and Bartow or Russell and Norvig as references.